Presentation is a bit differ from the title because our marketing prepare, I may say, a bit commercial presentation, so I changed it a bit. Actually, I completely changed it. And we will talk today about quality metrics. Okay. So all of you know that quality is the main thing, and you need to measure it. And many of you are customers of Elecart analyzers, and those who are working in codec development know very good about PSNR, SSIM, VMAF, whatever else. But we found that when we go to another market, to monitoring market, the old metrics which are good for codec developers does not work for operators. So let us start with the traditional metrics. So the most simple and most often used metric is PSNR. Actually, this is the pure difference between two videos, between two frames. I'm using this metric for almost 40 years, 35, and can understand what does it mean, but I may say that all these numbers, when PSNR is good or bad, is not 100% corresponds with human eyes. SSIM. SSIM is much better. It has a, something wrong with the formulas, but anyway. So SSIM is about 4 times longer formulas, but it corresponds much better with human eyes, but not perfect as well. VMAF. VMAF is much better, and again, about 10 times more CPU, need more CPU power to compute. It's much closer to human eyes, and I play with VMAF for almost a year and a half, and I may say that for those who do not need to calculate video metric for each pixel or for each block of a frame, VMAF is good enough. So when I preparing this presentation, I just pick a couple videos from my collection, which I'm sure show the bad sides of PSNR. But the results that I got surprised even me. I expect that for each frame, for each video, for each given PSNR, I may say what is the real quality of this video or of this frame. So I took a look on those 2 frames. PSNR, that's original on the right and compressed on the left. PSNR between those 2 frames is 27, which is actually completely bad. But usual consumer cannot find the difference between those 2 images. And take a look on another. And we have also PSNR 27 between those 2 images. And actually, what means PSNR? PSNR, on this slide, you see the pure difference between images. And PSNR just calculate this difference. And actually, from computer point of view, it is the same. But from our point of view, it's completely different. SSIM work better for those two images. It distinguishes it somehow. If PSNR told that both images are completely bad, SM tell that one is bad and another is full junk. But VMAF understand it normally. So for anybody who is not from codec development, who have no need to use, I don't know, adaptive quantization in codec development, I'd recommend to use VMAF measure. Well, but all those three measures, all those three measures are based on a source video. But very often operators need to know the quality of the video when they have no reference. So this is the no reference measure, EPSNR. Actually, the idea behind EPSNR is very simple. When we have compressed video, we know the coefficient and the quantizer. Say we have a coefficient equal to 5 and quantizer is 20. So the quantized coefficient will be 100. This means that original coefficient was somewhere in between 90 and 110. So if we add random number in this diapason for the quantized coefficient, we will receive an error somehow close to original error. And then we just calculate the PSNR between these randomly noised coefficients and decoded coefficients. And it provides more or less good estimation for real PSNR without source file. So here you may see comparison of PSNR and ePSNR. You may see that for high bit rates, it works fine, but for low bit rate, especially for P and B frames, especially for B frames. P frames more or less good, but B frames, you may see that it's a large difference between real PSNR and estimated PSNR. This is because those B frames have a lot of zero coefficients. And for zero coefficients, it's not white noise distribution. It is something close to Gaussian. But again, for badly predicted frames, it will be close to white noise. But for good predicted, when we have a lot of originally zero coefficients, it will be close to Gaussian. And we cannot distinguish while calculating it. So for low bit rates, it does not work good. And another problem that it's actually does not work good if we have a few transcoding in a row. So we can measure only, estimate PSNR only for the last transcoding in the row. But this works more or less good. About half a year ago, one young but very ambitious company asked us to help them with their project. Actually, they are going to encode and send over IP almost all satellite channels in the world, I guess. I do not know it from them, I just understand this. Something like 12 or 14,000 channels delivered over IP. And they need to compare quality with the content which is delivered through satellite. So what they found that the content provider provide them not exactly the same videos as provide to satellite distribution. So when they compare video received from satellite and video received from their delivery chain, they found that they was encoded, they were compressed from the different sources. So we tried to find how to compare those videos and how to say how good they are, how to compare it. So actually, we have some sort of source video, but not the same for both delivery channels. So we decided that we may calculate some metric and compare those metrics for the good quality and two videos with a bad quality, and make a decision which is better or which is worse. The problem also that, say, codec developers in the lab, they could do all this comparison very easy. They may do a dump of a video on the client side, put it in the lab, and compare one video to another. But when you have 12,000 channels, which are distributed over the world and which you need to compare, actually this does not work. It has to be automated somehow. So the idea was to get some metric, say one number per frame, few numbers per frame, and compare those two metrics for different files. First, we start with comparing Luma histograms. This is how looks Luma histogram for uncompressed image. Compared to the lungs of a heavy smoker. I'm sorry, this came from another presentation. Compared to heavily compressed image. Actually, you see that histograms are quite different. This is the difference. So we get some measure of quality of Luma histogram. And this is very good metric, but it does not work good enough for predicted frames. Again, we cannot distinguish very good predicted frame from badly predicted but highly quantized. But this metric gives us give us an idea of compression artifacts. So then we start to look for different non-reference metric, and I actually found that most of presented non-reference metrics can say probably this is not good quality, or probably this is good quality. All of them are based on calculating blockness or blur or whatever else. So we decided to calculate number of details. So if we have some sort of a source video, we may calculate number of details in the source video and compare it to number of details in the target video. How to calculate number of details in a video frame? It's apparently you need to do Fourier transform and calculate number of non-zero coefficients. This works, but again, this does not work for predicted frames. So we need to add motion estimation. Okay, I add motion estimation, and then decided that it's not that clever, just calculate number of non-zero coefficients. It's better to use some entropy encoder. But when we have motion estimation and Fourier transform and entropy encoder, what we have? we have the full video encoder, of course. And funny enough that if we use, I use just Elicard AVC encoder with a constant quantizer, with a low constant quantizer, and calculate output of the encoder, I mean bit output, which provide rough but very interesting metric of calculating details, of calculating number of details in a video. So actually we combine those three metrics, EPSNR, then based on Luma histogram, and got some sort of new metric which we called number of details ratio. We may calculate just number of details for image ND metric, and so here you may compare video 1 to video 2 by this ND metric, say 10,000 per second for video 1 and 9,000 per second for video 2, which means that roughly 10% difference. Or you may calculate this NDR metric, compare video 1 with some source video or video 2 with the source video. And you will get the simple measure in percent. So how much details are still in this video after the full chain of recompression. And interesting enough that we got the result very close to VMAF. And again, we compare here not full frame against full frame. We compare here 3 numbers per frame with another 3 numbers per frame from a different video. And we may compare the same way 2 videos encoded by different way from different source, but of course it has to be the same video, and compare it one against another. So here the numbers that we have a percentage for NDR metric compared to PSNR and compared to VMAF and SSIM. And 2 rows in bold correspond for those couple images that I show you in previous slides. So for the bad one, NDR is 2%, and for good one, NDR is 70%, which we may say that is good and complete junk. While VMAF shows about the same, and PSNR and SIM is not that good for them. With this type of metric, we may easily compare videos quality in this type of application. And currently, we are implementing this metric in our Boro monitoring solution. Right now, it's only EPSNR there, but in the next generation, probably to the end of this year, we will have also NDR metric there, so you may use it in your environment somehow. And yeah. So actually, okay, it's nothing. So actually that's it, and I'd like to answer your questions.
Thank you very much.
Very good, very interesting. I assume this metric varies based on the quality of prediction?
Yes, of course. Its metric works good for good codecs. If you take completely bad one, which do very bad motion estimation, it will not be such a good.
Right.
Actually, the motion estimation that we are using is I hope, is good enough. So corresponding codecs have to have about the same quality of motion estimation.
I'm saying to use this as a quality measurement that has some consistency wherever it is used. You have to have consistent settings for motion estimation, and obviously you can set an encoder to do more prediction, to try more things, have better motion estimation, less residual error.
Yeah, you are right, but it's not, actually it's not that big problem. Because, again, our customer, our potential customer here, they are asked to provide estimation from 1 to 10. And if we have just 10 grades, it works quite good.
But also the amount of calculation that you're doing, if you're already doing encoding, most of the work was already done in the encoder, so it's relatively low compute cost for this if you're already encoding.
Today we are using just software encoder to do this, but we are going to implement it in Intel-based encoder, hardware-based encoder, so cost of encoding will be very low. Something like estimation like 15 full HD streams in real time per one Core 7 CPU.
Very interesting.
Any other questions? Alex?
So, are you planning to publish this and allow for independent verification?
Well, sure. I will be very glad to provide you for early stage verification.
Thank you.
Great. So there's going to be an independent evaluation. Thank you very much, Andre.